Welcome to today's deep dive on Thursday, March 5th, 2026. We're so glad to have you with us. Today we're looking at a comprehensive analytical paper on curvature variable physics, or CVP.
Right, CVP.
Yeah, and our mission for you today is to figure out why the biggest roadblock to commercial fusion energy isn't really about building bigger hardware anymore. It has actually become this massive, highly complex cyber-physical control problem.
It really is a profound shift in how we approach nuclear fusion. For decades, the entire focus was just on constructing massive superconducting magnets or, finding more resilient plasma-facing materials.
Basically just trying to build a tougher box.
Exactly, a tougher box. But as that hardware has matured, the reality of keeping superheated, nonlinear plasma stable, it's moved from a physics challenge to a software challenge.
Okay, let's unpack this. To handle these incredibly chaotic plasmas, scientists are deploying artificial intelligence. Specifically, deep reinforcement learning is being used to control the fusion reactions in real time.
Yeah, it's incredible.
It is. Like over at the Swiss Plasma Center, AI is autonomously controlling 19 independent magnetic coils to mold plasma into these crazy snowflake and droplet shapes.
But that incredible algorithmic power brings us to a terrifying bottleneck. Unconstrained AI is mathematically brittle. If an AI algorithm strictly chases peak performance, say, optimizing purely to hold the plasma as long as possible without understanding the physical risks, it can encounter what we call out-of-distribution failures.
Meaning what exactly? Like the AI just gets confused.
Precisely. If the AI encounters a plasma behavior it never saw in its training data, an out-of-distribution failure, it might panic and make a wrong move. And at these extreme temperatures, a wrong move means instantly melting your multi-million-dollar reactor vessel.
Wait, but if you heavily restrict the AI to prevent that, aren't you crippling its ability to find new, better ways to hold the plasma?
You are, but safety absolutely has to trump optimization in a nuclear environment. What's fascinating here is how the CVP framework solves this exact tension. CVP introduces what it calls a safe manifold.
A safe manifold?
Right. You can think of it as a strict operating constitution for the control system. It fundamentally prohibits the AI from taking any actions that fall outside predefined, mathematically verifiable safety boundaries, regardless of any potential short-term performance gains.
So if the safe manifold is the constitution, how does it actually police the plasma? Traditional sensors must just melt or degrade in that kind of radiation. Here's where it gets really interesting. Instead of relying on those fragile raw sensors, CVP uses something called 4D spatiotemporal reconstruction.
Which sounds incredibly sci-fi.
It totally does, but it basically maps the magnetic field in 3D space plus time, which is your fourth dimension. It's essentially looking for dynamic wrinkles or turbulence forming in real time, calculating exactly where that disorder is aggregating so the system can smooth it out.
And it does all of this without violating the safety constraints of the hardware. But mapping it isn't enough. You have to prove it works.
Right. So how do you actually prove to regulators that this AI won't go rogue?
That is where the TVR framework comes in. Test, evaluation, verification, replication. It requires cryptographically secure proof bundles for all operational data. Basically, it acts as an unalterable digital black box.
So it's locking the data down permanently.
Exactly. This guarantees exact local recovery, meaning if you turn the actuator off, the plasma must revert precisely to its baseline state. It permanently ends the fusion industry's reliance on unreplicable hero shots.
Oh, those are those lucky, anomalous experimental runs that look great on paper but are impossible to recreate, right?
Spot on. TVR demands perfect, verifiable replication.
So why should you care about all this? Beyond the promise of clean energy, CVP allows for something called micro-experiment batching. It's like, instead of crashing 100 actual cars to test a bumper, you gently tap the bumper in 100 different ways during a single drive.
That's a great way to visualize it.
Instead of spending millions on separate, risky reactor shots, scientists can run tiny, perfectly safe mathematical perturbations during a single run. The industry saves a fortune while accelerating development.
If we connect this to the bigger picture, agencies like the Nuclear Regulatory Commission are going to be paying very close attention to this. As we move closer to grid-connected commercial power plants, regulatory bodies will inevitably require this exact type of verifiable software governance. You simply cannot deploy a black box AI to run a nuclear facility. You need deterministic, highly auditable boundaries.
So what does this all mean? It means that scaling fusion energy to power our world now fundamentally depends on rigid software governance. It's no longer just a quest to build bigger magnets. It's about proving our digital control systems are absolutely verifiably safe.
This raises an important question. If artificial intelligence requires cryptographically verified boundaries and a safe manifold to safely run a fusion reactor, how might these exact same principles be urgently required for AI systems managing our national power grids or automated logistics networks?
That is a massive thought to leave you with and definitely something to chew on. Thank you so much for joining us for today's deep dive. We will catch you next time.